Hello. Day 2 homework for, this isn't really day 2, but it's kind of like day 1 of our thing, but I don't even remember in this little vector module from the College Board what the day 1 homework was, but it was too easy for you guys, and just unnecessary, I think. So we know now to find these from your notes that dy dx, if you're trying to find that for some parametric equations where x and y are given in terms of the parameter t, then you just need to do what, I don't know, maybe seems, if not obvious, at least like pretty clear. Less obvious is the how to find the second derivative, right? That's, you got to take the derivative with respect to time of dy dx, and of course you found the dy dx by doing this, and then you have to divide by dx dt, and I think I went through that in the notes for you. Why is that? It doesn't come up a whole heck of a lot on the old AP test, but it does every once in a while. Like there's a quick little multiple choice question where you have to know that, and I could see a way it could be folded into a free response question, although I have never seen that. So anyway, it's something we need to know. It's a little bit of calculus esoterica. So in the first one, number 1, we have, I'm going to write y equals first just because that's going to be on top. So dy dt is 2t plus 6, and and x is t squared, so dx dt is 2t. So that means that dy dx is this over this. And you might be like, yeah, I'm not going to simplify because my calculus teacher told me I don't have to. Well, you don't have to, but we do have to find the second derivative, we have to take the derivative of that. So actually that's going to be beneficial to us to simplify, right? Just dividing through by that monomial there. So there's our first derivative, and then the second derivative is the t derivative of this, which would be negative 3t to the negative 2, divided by dx dt. And that one you can leave unsimplified if you want, but it would be that. There's my dy dt and my dx dt for these parametric equations. Make sure I copied everything down right. Looks good. So that means that dy dx would be 6t squared minus 2t over 2t. And I'm going to simplify that because that's going to be helpful. And then the second derivative is the derivative of this over dx dt. And that's simplified enough for me. Number 3. While I'm writing these down, it might be good idea to talk about, like, what are these things? Like, what's a parametric equation anyway? Well, parametric equations, t is just some parameter, but often, like in the real world, when parametric equations are useful for modeling things, the parameter t is time. Now, it's not really by accident that the letter t was chosen there. So what does it mean? Well, like in physics, for example, we might have like position, like horizontal position and vertical position as functions of time like this. That's negative, that's 1/2 a right there. So these are actually the parametric equations that might describe something in two-dimensional projectile motion. So if you plug in 0, you get 0, 0. And then if you plug in 1, you get 10. And then you plug in, I guess I'd get something kind of small there, wouldn't I? So I guess I'd have to plug in things that are smaller than that to see what's going on. But what you're going to find is that you get a parabolic arc like this. But the difference is with parametric equations, if you're thinking to yourself, well, we already did that in physics. No, we didn't actually do this in physics. What we did was we graphed y versus t and x versus t and looked at those graphs. So this is a graph of the actual path or the trajectory of this, in this case, projectile. And we might have like t equals 0, t equals 1. So this has kind of like a directionality to it that other graphs don't have. And if you're like, well, yeah, of course it just goes this way. But you could set up parametric equations so that it would go this way, that it would be, the flow of this thing would be times 0, 1, 2, and so on. So it's really useful to be able to have this picture of the xy and also have the time sort of coded into that. So this is really, it's kind of like a three-dimensional graph in the sense that it's keeping track of 3 different things if you put those little markers in. And I think probably in pre-calculus you learned about how to eliminate the parameter. I can't remember if I talked about this in the notes or not, but we really don't care about that. That's not the game that we want to play. We want the parameter to be there. So when we start doing this calculus of parametric equations, what are we finding? When we find dy dx, what is that? That's the slope of the path. It's the slope of the trajectory at whatever time. And then what are we finding when we are finding this? It's the concavity of the path, right? That is what we are finding. All right, blah, blah, blah. So 3, I got those written down, and before I distracted myself with that little soliloquy about parametric stuff, I was doing this. All right, so dy dx is this over this. Just remind you that I'm writing the y first and the x first just for organizational purposes. I think that works for me. Okay, so I'm going to divide through by this monomial. So 6 over 1/2 is 12 t to the 3/2 plus 4 t to the 1/2. Right? I learned that in an algebra class that I took a long time ago, how to do that. Maybe you know how to do it too. And now, to find the second derivative, I need to take the derivative of this and then divide by that. And when I do that, I don't think I'm going to simplify that. You could, but whatever. So 3/2 times 12 is 18. I learned that when I was in like kindergarten or something. No, probably not. T to the 1/2 plus 2t to the negative 1/2 over 1/2 t to the negative 1/2. Okay, fine, I'll simplify it. So it's going to be 36 t plus 4. I guess that's worth simplifying because like that compared to that, yeah, fine. You win. Okay, so y is t squared plus t, x is equal to natural log of t, so dy dx is equal to 2t plus 1, and, oops, just kidding, that's dy dt. dx dt is 1 over t, so dy dx is this over this, which is 2t squared plus t, dividing by a fraction, same as the multiplying by the reciprocal. And then the second derivative, take the derivative of that with respect to t, and then divide by dx dt again, and that's 4t squared plus t. Groovy. All right. Y equals 4 cosine t minus 1. X is 3 sine t plus 2. dy dt is going to be negative 4 sine t. dx dt is equal to 3 cosine t. So dy dt, dy dx, just kidding, dy dx is equal to that over that. I'm going to call that, well, I'll write it like this first. I'm not going to skip any steps. If you wanted to simplify that, that's negative 4/3 tangent t, right? Because trig. And then that, since I have that nicely simplified there, is just going to be negative 4/3 times the secant squared of t over 3 cosine t. Do you feel like you want to simplify that? Well, if you were going to, since this is secant is 1 over cosine, so depending on how you want to deal with this, you could do negative 4/9 secant cubed t, right? Because the 1 over cosine, that's another secant. And pile in with that one. Or you could do negative 4/9 cosine cubed t would work too. Okay, I think that's the end of that portion of today's program. Number 6. I think I might have room to do this here. Let's see how it goes. Find dy dt in terms of t. So that's a y. That looks like a v. Sorry about that. I wonder if maybe your copy looks better than that. So dy dt is going to be 3t squared minus 2t, and dx dt is going to be 2t plus 1. So dy dx, 3t squared minus 2t over 2t plus 1. Nothing you can do to simplify that. And then find an equation of the tangent line to C, the curve defined by these parametric equations, at the point where time is 2. Okay, so I've written many equations for many tangent lines. What I need the point, and I need slope. And then I can write it in point-slope form, right? So what is the point where t equals 2? Well, when t is 2, the x-coordinate is 4 plus 2 is 6 minus 1 is 5. And the y-coordinate when t is 2 is 8 minus 4. And the slope when t equals 2 is, let's see, 3t squared, that's 12 minus 4 over 4 plus 1. And that's all the info that I need. Now I can just write it in point slope form. No problem. Okay. Same deal with number 7, playing the same game. So dy dt is 3 cosine t. Dx dt is equal to negative 2 sine t. So dy dx is negative 3/2. I don't know, we want to call that cotangent. I don't know if there's going to be any for like figuring this out. I'm, of course, much more conversant with just cosines and sines than just knowing right off the top of my head, although cotangent's not a hard one. So let's see what we can do here. I need a point, and I need me slope at time pi over 4. So the cosine of pi over 4 is the square root of 2 over 2. The sine of pi over 4 is also square root of 2 over 2. And the slope is cosine over sine times negative 3/2, so that's just negative 3/2 because those two, the cosine and sine, are equal to each other. So both tangent and cotangent are equal to 1 at pi over 4. So I can write the equation for my line now. Y plus the square root of 2 is equal to the slope times x minus 3 root 2 over 2. In problems 8 through 10, we want to find dy dx again, and then find all points of horizontal and vertical tangency. And it says all points, right? So we can find the t values that make the horizontal. That will be when the top of the slope is equal to 0, and this is where the bottom of the slope is equal to 0. And of course, all these things have tops and bottoms because of the way we're constructing them. So I think I probably need more space than what I've got on this sheet here. You know, I reuse all my paper as much as I possibly can to do the least amount of damage to the world. So 8 is going to be going to find dy dt and dx dt. So let's see, that's going to be 2t minus 4 and 1. So horizontal tangent lines happen when the numerator of the slope is equal to 0. And I don't need to do any fancy algebra to see that that's going to happen at time 2. And vertical tangent lines happen when the denominator is equal to 0, and that happens at nowhere. Okay, so at t equals 2, the point is, now I'm going back and plugging the 2 in to find my x and my y coordinates. Right? Because it asked for what's the point. Not what's the t value, but what's the actual point. So that's why I had to go back and do that. Let's do that again, because it was so fun. dy dt is 3t squared minus 3, and dx dt is 2t minus 1. So horizontal tangent lines at t is equal to plus or minus 1. Now you might be like, wait, negative time? What's up with that? Nobody told us here that the t parameter actually stands for time and that it's only times greater than or equal to 0. So we have to allow for all possible t values, and that's going to be at 1/2. Okay, so plugging t equals -1, what do I get there? When I plug -1 into the x, I get 1 plus 1 plus 1 is 3. And when I plug the -1 into the y, I get -1 plus 3 is 2. And at t equals +1, I get 1 minus 1 plus 1 is 1. And the y-coordinate is 1 minus 3, which is -2. I think I did that all right, hopefully. If there's any mistakes in any of this stuff, it's just silly stuff that you guys can easily fix. And then at t equals 1/2, when I plug 1/2, fractions, let's see, I get 1/4 minus 1/2, which is -1/4, plus 1, which is 3/4. Hope I'm okay here. And then 1/2 cubed is 1/8 minus 3/2. 1/8, scratch work, 1/8 minus 3/2, which is the same as 12/8. So -11/8, I think. Hope that's right. And number 10, same game again, looking for the HTLs and the VTLs, horizontal and vertical tangent lines. dy dt is going to be 4 cosine t, and dx dt is going to be -2 sine t. Horizontal tangent line, when the top dy dt is equal to 0, that's going to happen at, and we're going from 0 to 2 pi, including 0, but not including 2 pi. So where's the cosine function equal to 0? It's equal to 0 at pi over 2 and 3 pi over 2. The 4 doesn't make any difference because it's not in there. It's just the period of this is still 2 pi. Same here. The -2 doesn't matter. So the vertical tangent lines are going to happen when the sine function is equal to 0. That's at time 0 and pi, and it would be 2 pi also, but the 2 pi is not included in the interval, so just at 0 and pi. And now I need to find my points. So when I plug in excuse me, pi over 2 into the original things, and my x, the cosine of pi over 2 is 0, so that's just 3. And then the sine of pi over 2 is 1, so that's 5. That's at t equals pi over 2. At t equals 3 pi over 2, the cosine of 3 pi over 2 is 0. And the sine of 3 pi over 2 is -1. How did I get 5 here? That seems wrong. -1. Yeah, that should be 3, right? That should have been -1 plus 4. Right? Okay. What are the points where we have vertical tangent lines? That's at 0 and pi. So when I plug in 0, the cosine of 0 is 1, so that's 5, comma, plug in 0, -1, and then when I plug in pi, the cosine of pi is -1, So that's going to be 1, and the sine of pi is 0, so that's going to be negative 1. All right. I'm just going to make a quick sketch of this, what these points look like, and talk about, we don't want to be completely oblivious to what's going on here. So 3, 3, that's here, 3, negative 5. Those are the places where we have horizontal tangent lines. So whatever the curve's doing, it's horizontal there and there. And then 5, negative 1, and 1, negative 1. That's where it's vertical. So look at that. What do you think this curve looks like? Well, looks like that. This is an ellipse, and it's not like kind of like an ellipse. It is an ellipse. It's an ellipse, if you look at the original. It's an ellipse with a center at 3, negative 1. 3, negative 1. And these are like remember the A and the B values when you're doing ellipses in, I guess in pre-calc you do that. So it turns out parametric equations are really nice ways to define ellipses and circles and things like that. So that's kind of cool. All right, so 11 and 12 we just want to write the integral expressions that represent the length of the arc of the curve over the given interval. So these often turn out to be integrals that are not easy to actually solve. So they either happen in calculator active problems, or sometimes we're just asked, like we are being asked to do here, to just write the integral expression and then walk away. So that's from your notes. So that's how you find the length. It's basically like the Pythagorean theorem. So hopefully that's somewhat intuitive. So here I need the integral from time 0 to 2, square root of what's the dx dt would be 2t squared, plus dy dt is 3t squared, and don't need to do any more than that. And then last here, I need the square root of dx dt would be 2e to the 2t. Don't forget the chain rule there. 2e to the 2t squared plus, that's just 3 squared.